369. 3, no, that's it. That's the way it goes. The steel one is also plate design. So, rolling on to plate design. So when we talk about holes in any steel member, if it's a centre to centre CC dimension, lengthwise, that is called the pitch. If it is across a member, we call that cross centres. The end distance is the distance to the end of the member. The edge distance, being the distance to the edge of the member. Both of those are from the centre line to the edge, or centre line to the end. And the same goes for an angle, except that with an angle we have something called a back mark. And the back mark is where the angle fits up against a wall or another steel member, and the back mark is explained there. I have a question on the back mark in the test. The main reason why we do these calculations, if you look down a little bit at this next diagram, is if the distance between the holes, which we call the pitch, is 32 times the thickness, or 300 millimetres, whichever one is the least, is your calculation. If that is greater than that, then you get the buckling occurring. So in other words, when you're doing a plate design, the thickness of the plate is important. When we multiply 32 times the thickness, let's say it's a 10 mil plate, that's 320, which is bigger than 300. So therefore, 300 becomes our minimum. If it's over that, we run the risk of buckling. We also have a maximum distance, we have a distance here where the holes can't get too close or too close to the edge. So I guess that one at the top is a maximum distance, this one down here is a minimum distance. And that is based on 2D, where D equals the diameter of the bulk, not the hole. That's a little bit confusing, but that's what the calculation is based on. If you don't, and you make those closer together or closer to the end, you're going to get what's called bursting on a plate. So let's look at a basic plate design and see if I can relate that.
Just with the edge and the end.
Yep.
So can you just show where the edge is and where the end is?
It's mostly relating to a beam. You have a beam like that. So the end of the beam is the end we're looking at, right there. So that's the end distance from the last hole to the end. So the minimum would be 2.5 times the diameter of the bolt that's going into the hole. Okay? Edge is to the edge of the beam, the side of the beam. Okay?
And this is the last one.
Yep. Yep. So using this analogy here, I'm going to do a plate design over there for in terms of, I don't see, we do the and I'm going to, look at that, my drawing's still there from last week. So I'm just going to randomly make up some numbers here. We have a plate which is, let me see, 370, and over here it is 400. The engineer has decided that there will be 4 bolts where possible. That is an 18mm bolt hole. The plate is 10mm thick. What we need to calculate is those distances there and these distances here. So the first thing we do is we work out our maximum. So our maximum equals 32t, which equals 32 times 10, which equals 320. However, because the maximum is 300 in all cases, we have to go to 300. So our maximum is 300, what's our minimum? Minimum is 2.5 times the diameter of the bolt. So it's 2.5 times what's the diameter of the bolt?
15. Is the diameter of the bolt same as the diameter of the bolt hole?
15 is close. 18 is not right.
16.
16, yeah. With the bolt in steel, this isn't wood. With wood, we drill a hole and we put the same size bolt through. If it's kind of a little bit not working, we just hammer it through and then we screw it on, right? With a bolt for steel, because steel's not very forgiving, we always allow 1mm all the way around. So we've got an 18mm bolt hole, 1mm either side,
This is 16
means
millimeters.
a 16mm bolt.
Yeah.
So it's 2.5 times 16, which equals 40. So that is our minimum of 40, right? When we do bolting, it's no different than when you were younger and you used to watch your grandmother do the quilting. And it's like reinforcing steel as well. You push it as far to the edge as possible. So therefore, the first thing we do is we do our minimum. So we come along with our, I'll do this in green or red, and we do our 40 first. So we do 40 here. We do 40 here, so what's left? 40 and 40 is 80, minus that makes 290, right? We compare that with our minimum over here, so that gets the big Nike thick. We come over here, we go 40, 40 minus 400 makes 320. We compare that with this, and we've got a problem. So then we get out our green pen, we cross that out, and we go 300, we cross that out, and that goes to 50, we cross that out, and that goes to 50. And that is the difference, that is a plate design. Okay? So by doing that, I've shown you that this one stays the same, we're all happy with it. This one needed to be adjusted because it was too much. Always start with your minimum. There will be 3 questions on that in the exam, test, sorry. And I will go over that again with 3 more examples.
You actually need bigger bolts on that side.
No, same size bolt, still 16mm bolts.
So how can you make it 50?
16.
And that means it's about 18.
The hole is 18. See? Yeah. The hole is 18 and the bolt is 16. Right? Now here's your dilemma for your assignment. I haven't, if for those that have have looked in the assignment over the last week, I haven't given you a plate size. And there's a very good reason for that, because I'm expecting you to make up your own plate size. And I would expect that it isn't a good idea to make the same plate size as your friend, because you'll end up with the same total as your friend on the assignment, and I'll start to be thinking that, hold on, someone's copying someone here, if you know what I'm talking about. So, I suggest you come up with a plate design which is a little bit more original, like, I don't know, 396 by 403. Okay? Still use the same method to calculate where the holes are. So here's your dilemma. You've got an assignment 3 due on the second week of the holidays.
This week, actually.
Yeah, the middle week, the middle Sunday of the holidays. Yeah. And for that you need to do a steel schedule. And on that schedule is a plate. And you have to come up with a number for the plate to work out the weight of the plate. There's 1, 2, 3, 4, 5, 6, 7, 8 of them. Now, I don't care what your numbers are, I'm checking your maths, right, to see that your plate weighs what you say it weighs. If it's correct, you'll get your half a mark, whatever I allocate to that section of the steel. However, you are not allowed to change it for assignment 4. On assignment 4, you have to do a plate detail. The holes will be completely wrong, or could be wrong. Therefore, you'll lose 1 mark on your detail, because I'm going to make you detail the plate. And on top of that, you'll lose marks because every time you call the plate up, it'll be wrong. So what you need to do for assignment 3 is calculate that the holes are going to work. And then you'll be fine. Now, just to recap, you have a column coming down here like this onto a plate which sits on the concrete like that. And you need to put 2 bolts, 4 altogether, through the plate. So looking down on that, you have got a situation like this where the plate sits here and your column sits like that, and you've got to get some bolts into here, here, here and here without breaching your maximum or your minimum. It's not as hard as you think. The problem you've got is, one student said to me, oh, that's easy. I'll just make it like this big and it'll still work. I said, no, it won't still work, because if you make it that big, you'll need more holes, and I've only asked for 4 bolts. Client's not going to be very happy about that. It's going to need more bolt holes, more bolts, and pay for more steel.
Is that plate welded to the column?
Yeah, it's welded, the plate is welded around here, we'll talk about that in a minute. So around this is a weld. So you can't put your holes too close to the weld, or you won't be able to get your spanner in, tighten it up, or socket. So you're restricted in terms of getting it too close to the weld. The weld, I'm going to tell you what that weld is before the lecture's out. It's a 6mm fillet weld, so 6 mils. So let's say 10 mils clear of that, and you've got your other restrictions up the top as well. So I would suggest that there are a lot of different plate sizes you can use that will work, and there's a whole lot that won't work. And there will be students that email me after they've done assignment 3, please can I change my plate size? No. Okay? But they would have already got half a mark out of me for getting the plate correct on the calculations. So that's your dilemma. Take the half a mark off it, and then it cuts you out of your detail. So that detail looking down here, which will be a section view, will be one of the details that you have to draw for me. I'll talk about that in the lab later on. Welding. There's some more notes there on bolting. These are ways of detailing bolts and bolt holes. And some examples of how we look up different sizes on channels and angles. You don't have to use this. This was for another assignment, but it's in there for information only. Common terms. I would revise this if I was you. For example, the lintel, the chock, girt, which is a welded member on the side of a building for exterior weatherboards or sheathing. A splice, which is for lengthening and not strengthening but lengthening